Hi, class. This is number 2 in 9.5 homework. Okay. Ouch. Oh, ouch. Sorry. Okay. It says the proportion of people who own cats is 40%. A veterinarian believes this proportion is larger than 40% and surveys 500 people. Okay. The proportion of people that own cats is 40%. A veterinarian believes this proportion is larger than 40% and surveys 500 people. Test the veterinarian's claim at the alpha equals 0.025 level of significance. Is it safe to assume that the population is less than 5% of all subjects in the is that the sample size, n, and little n is always sample size, large n is the number in your samples, in the population, or that capital N, So the sample size is 500, and they're talking about people who own cats. I don't know if they're talking about like people who own cats, at his veterinarian's office, or whether they're talking about the people who own cats, in the state of California, or whether they're talking about people who own cats in the, what am I thinking of the, the United States, or what he's really thinking about as his population, because he should state that very clearly, and they should actually give us the number in the population of interest, but they don't. So for usually this problem, they're just putting it in there to remind you that that's something you really have to consider in real life. And they're just we just kind of wave it and be like, yes, the answer is yes here. Because they don't even give us, a proper way to really calculate this. If we knew the number of people in the total population of interest here, then we would take 5% of that and make sure that it's larger than the sample size. But we can't do that. So we just have to say yes in this first part. Then it says verify that n times p times 1 minus p is greater than or equal to 10. So the n is the number in our sample, which is 500, which that's a large number to begin with. So I'm thinking this is probably going to be greater than 10, but 500 times p is believed to be population proportion, which is 40%. So it's, so I never write it as a percent. I always write it as a decimal. So 500 times 0.40 times 1 minus 0.40, and we just put that into the calculator. Make sure that you do 1 minus 0.40, get an answer, then multiply that answer times by this answer times by this answer. Or if you do it, make sure to put multiplication symbols in the calculator, and make sure to put parentheses. Most calculators will do order of operations for you if you put parentheses around that, but some of them, not all of them, do. And I honestly, I do not trust my calculator to do order operations, because sometimes they don't always do it correctly. So let's do this on Class Calc. Do practice this and make sure that you're getting exactly the same answer as I am, because you may not get the same answer. So 500 times by 0.40 times by 1 minus 0.40 is equal to 120. Let's see how we got that 120. And just we can kind of sort of even double check that. If I took half of, when I multiply 40% times 500, that would be 250, about 250, that's 40%, about half, of 500, so it's like 250. And then we multiply by 1 minus 0.4, that's 0.6. So it's kind of like multiplying by 50% again. And then, so that would be 125. So 120 sounds really, that answer sounds correct. So I think our answer for this part is going to be 120. Let me see. then they say the null alternative hypothesis are, now the alternative hypothesis is always probably the easiest to figure out from the wording, and we're looking for words like larger than, more than, less than, right? Decreased, increased. We're looking for that word, okay? So here it says a veterinarian believes or that the proportion is larger than, right? So if we write that literally as we hear it, proportion P larger than, the alligator's mouth goes toward the P for 40%, so written as decimal 0.40. So right, like I literally turned everything into words, each word here into the mathematical symbol to represent it, and it's the P greater than 4.40. Okay, so that's the one we want. So I don't want any of these that use this mu. That's talking about the means. These are wrong. These are all wrong. Okay, so now we're looking at those three, and the only one that has where the alligator's mouth is facing toward the P is this one right here. So that one must be the correct one. Now, let me talk about the null hypothesis. Typically, the null hypothesis, you don't have to think about too much to figure out what the null hypothesis is, because the null hypothesis is, okay, it's either going to be one of two things depending on the person who wrote this problem and the textbook they used. It could be either the exact expression, you know, P and the 40 are 0.40 are the exact expression. Let me try to move down here. Or exact expression except for the inequality turns to equals. Or it could be exactly the opposite expression. So if this says P greater than 0.4, well, what's the opposite of greater than 0.4? Equal to or less than. So then the alligator's mouth in the null hypothesis might be facing the other direction. So this one's facing to the left, and the mouth will face to the right with the 0.4. And then it always, the null hypothesis is always going to be either just equals, just plain equals, or it might be like greater than or equal to, but it always has the equal sign in it somewhere, whether it's whether it's actually just equals by itself, or whether it's greater than or equal to, you know, whether it's this one or this one, but the equals sign is, or this one is always part of the null hypothesis. So like I said, either you take the exact letter and the exact number, and those are the exact numbers and letters that need to be in the null hypothesis that you used in the alternative hypothesis. But the only thing that's different is the inequality became equals, or the inequality became equals and opposite of what you see in the alternative hypothesis. Okay, so that's what's happening in this situation. It's equal and opposite of the alternative hypothesis. Okay, so that is the null alternative hypothesis. Next, they said the test is, now this is pretty simple. We just look at the ulterior hypothesis, and whatever, you kind of make an arrow, you know, out of the ulterior hypothesis, and the direction the arrow is facing, that's the type of test we're doing. So it's facing to the right, and maybe you might be seeing a mirror image of me, so maybe you're seeing me point to the left, but it's okay. It's pointing to the right. Look, this is the ulterior hypothesis in this case is pointing to the right. So this is a right tail test. And sometimes that becomes really valuable because you don't know where to shade. And when you do your picture, and you have to make sure you shade the right tail in a right tail test. All right, next, let's draw. Let's go ahead and draw the picture. Like I said, in your final on your actual test, you will be asked to draw the picture of what they're talking about. So Okay, so here's what it goes. Based on a sample of 500 people, 49% own cats. Calculate a statistic, round to 2 decimal places. Okay. Okay, so the middle here is 0.40. I'm drawing right here. What I'm drawing is I'm drawing the sampling distribution of the sample proportion. Remember that the mean of that distribution is just equal to the proportion, population proportion, 0.40 in this case, and the standard deviation of that distribution, of the sampling distribution, the sample proportion, is equal to 1 or p times 1 minus p all over the square root of n, I believe, right? Isn't that the formula for the standard deviation? So I'm not going to worry about the standard calculating standard deviation, but I am going to place the mean just so I know where it is. But then 4.9, and now what I do is I take the sample mean and I label it, because it's a right tail test, it should be in the right side of the mean. And in the tail, if see 0.49, in order for us to prove our case that it's more, the proportion is bigger than 40%, we have to have an extremely rare sample proportion that's really large and different than 40%. So we want to find, what we're going to do here is we're going to calculate the probability that I'm going to get a sample that is 0.49 or larger. So what is the probability of me getting a sample basically that strange or even stranger, with the known that I believe that the mean here is 0.40. So this area under the curve is my p-value. This number that's serving as the cutoff as to where the shading along the x-axis is starting and stopping, this is my lower bound. That number is actually the sample proportion, or it is a p hat. That's the proportion coming from the sample. Right, and this is, I'm labeling all of this so that you guys know what numbers to put where on your graph. Okay, this number, that is actually the population proportion, that's p. That is the proportion, when they're talking about the whole population of interest, that's the proportion they believe to be true at the moment. Okay, this is the one that they got from their sample, and I think, hey, this is evidence to prove that the sample proportion, population mean, p, population proportion, p, is actually greater than 0.4. So they're thinking, okay, well, the distribution should be over here. If this is a really uncommon, very unlikely, almost impossible to get sample, then we'll think maybe this is actually a more common sample than if the two population proportion was like 0.48, then 0.49 would be a more common sample because it's closer to the population proportion. Because most of the samples are going to have the same proportion as the actual population here, which is 0.4. So we expect most of these sample proportions, to be really close to 0.4. And now it's 0.49. So we know it's unusual, unusually larger than 0.4. But how really strange is it? And since we learned from previous chapters that we can actually calculate the probability of getting a particular sample, we could calculate this p-value doing the old method that you learned in chapter 7. You could do normal CDF, provided that this is normally distributed, and you could do your lower bound 0.49, your upper bound positive infinity, and you could do the normal CDF. The mean is 0.40, and the standard deviation, we could calculate the standard deviation of this, like using that formula. like P, which is 0.40, 1 minus P all over the N, which is 500. And we could calculate, literally the probability of getting a 0.49 sample or more. Or we can just use our one prop z-test. I believe it is the one prop z-test will also just go more directly, just straight to the answer. This one, you kind of have to calculate. If you did use that calculation normal CDF, I'm just saying, I'm just connecting the concepts that we were learning from last section to this section, that we could do there's another way to find the p-value, but the faster way to do it is one prop z-test. This one just kind of allows you to put exactly the information they're given in the problem straight in, and with few previous calculations that you do. Hi, Michelle. Nice to have you with us.
Hi, how's it going?
Good, doing good. So I'm just going to finish up number 2. I'm doing it. Sorry, Hannah.
No, you're fine.
Thank you. So I was just explaining that, I was just actually drawing this picture, and this is important because you are going to have to draw a picture like this on the actual test. And you want to be able to draw the p-value and explain what is this p-value, what are the numbers on the x-axis and everything like that. And see, in this problem, they believe that, let me scroll up. It says the proportion of people that own cats is 40%. A veterinarian believes the proportion is actually larger than 40% and surveys 500 people. Makes a test the claim at alpha equals 0.25. And so we stated the null hypothesis. It's we believe that the proportion is larger than 0.4. And then now they went ahead and did a sample based on a sample of 500. 49% of those people in that sample, which they're giving us, what we call a p-hat. That's the proportion coming from the sample. So 49% of those 500 people owned cats, and they said calculate the test statistic. I'm not going to worry about calculating a test statistic. Most calculators automatically just calculate the test statistic along with the p-value. So we'll just go straight to finding the p-value, and then we can find a test statistic. It'll just fall out of the calculation. It'll just be also something that the computer just spits out will be that test statistic event. So I'm not going to stress too much about that. But I am going to draw this picture that see what happened is we want to find out really what is the likelihood of getting a sample that of 500 people such that 49% own cats. If the true population proportion, that means out of all the people of interest that we're looking at, 40% own cats. 49% is quite a bit bigger than 40%. So we obviously ran into more people in this particular sample that had cats than we'd see in the typical population. So it is a little concerning. Why are we at 49? And if the true population is 40% people like cats, and this is a true random sample of the population and it's representative of the population, we would expect it to be very close to 40% as well. So it being 49% is kind of a concern. It's like, well, maybe the true population proportion is not 40%. Maybe 45% of people actually own cats and not 40% like we originally had thought. And we're going to really believe that if 49% is so unlikely to happen. If us getting a sample back of 500 people and having 49% of them own cats, if that's extremely unlikely, if it's so unlikely, like it's like them winning the millionaire or whatever, or it's just impossible almost to happen, then we're definitely going to say, hey, we don't think that the original population proportion is 40%. We think it's more. So we have to go ahead and actually calculate that probability of getting a sample of 500 people with 49% of them owning cats. So we learned from the last sections that we can calculate the probability of getting a certain sample back with a certain characteristic. Remember, we drew the sampling distribution, in this case, because we're talking about proportions, of the sample proportion. And we talked about in the last chapters, it's equal to the mean of the p hat was equal to just p, and the standard deviation of the p hats was equal to, I believe it was P1 minus P all over N. And you don't really have to remember these two formulas, except for the first one. You kind of need to remember the first one, because that's why the mean of this picture is the sampling distribution, the sample mean, of the sample proportion. So these are all proportions along the x-axis. The center where that peak is happening, that is this 0.4 that's coming from our null hypothesis. So that value that's where that's coming from. And then the 0.49, where the shading is starting along the x-axis, that 0.49 is coming from the sample proportion. That's where this value is coming from. And then the p-value is actually the area under the curve. And because it's a right tail test, it's to the right of this 0.49. And I went over earlier that, like, how do we know if it's a right tail test, or how do we know which side to shade when we come to this picture? Well, the arrow in the ulterior hypothesis is actually telling you what type of test it is. So it's pointing, if you make an arrow out of that inequality symbol, it's pointing to the right. So that would make it a right tail test. And that would also make it, because we just put the sample proportion on the graph, and then we know to shade to the right, because those are we're trying to find the probability of it being 0.49 or larger. And that's where our population proportions would be 0.49 or larger, is in that region to the right of 0.49, because as we go from left to right, the numbers are getting larger. So we know this is our p-value. So now that's the picture that we want. So just a reminder of where all the picture is coming from is that the same number coming from the ulterior hypothesis is going in the center of that distribution. And that's the same for mean problems as well. If we're talking about a mean problem, this is a proportion problem. But then the sample proportion that's coming from the sample, that's the proportion coming from the sample, that's where the shading starts. That's another value along the x-axis. And then this area under the curve in a right tail test to the right of that value is our p-value. And we could find that p-value the old-fashioned way that we would have found it in chapter 7 would be normal CDF. 0.49 is our lower bound. Our upper bound is positive infinity. We put our mean and standard deviation in, and we would be able to find the same p-value. Now in this section, we're learning that instead of doing this normal CDF to find the p-value, we can go straight to the answer more quickly by using a one prop z-test. But this one prop z-test also gives us the same p-value that we would get if we did normal CDF, 0.49, and the lower bound, upper bound, all that we did in the previous sections. This new test is just a little bit faster, and we don't have to calculate like the standard deviation. It does that for us. And it's just, we don't have to think about it quite as much. And so it's a just faster way to the final answer. So that's why we just don't use that. But that is the way that we would find that p-value. And that's hopefully, what makes that p-value more understandable to you, because it is the probability of me getting a sample as large as that or larger. So now that we're, hopefully you guys are all understanding the picture, and hopefully you guys are all like understanding the p-value really well. Now let's actually calculate this z and p-value. So like I said, we go to the calculator. Well, we do have to make sure that we ask, is this a mean problem? Because if it's a mean problem, we need to use a t-test. But if it's a proportion problem, then we need to use a one prop z-test. So this is a proportion problem. It is pretty clearly stated in this particular problem, because it says the proportion of people that own cats is 40%. So right away, they're talking about a proportion, right? And then they say it believes the proportion is larger. So literally, they're stating here, again, they're talking about the proportion being larger or not. They're not talking about a mean or average being larger, right? So we know it's a proportion problem. And and so now we just have to find, this is the easy part. We just have to find the Z and P on the calculator, and we just have to enter things in the calculator and we'll be good. So I go to the one prop Z test. I go to stats tests, and then I go to one prop Z test. It tells me what I need to enter. Anytime you have a sub-zero on any value like that, it's a value coming from the null hypothesis. The null means like at zero, at time zero. I believe it's a physics term, and I don't know what, I believe null is like German for nothing or zero, or so like I'm not sure which but that's what they're saying. They're saying, so this little zero, and like they say the H zero, this is a P zero, and you'll see the mu zero. They're all, when you have a sub-zero, it's telling you, hey, it's from the null hypothesis. So this proportion from the null hypothesis, so we look back at what it is the proportion from the null hypothesis, or alternative hypothesis, because the alternative hypothesis and the null hypothesis are actually going to have the same number there. And it's 0.4. So that's the first number that they want us to enter to do this test. .4. And then the X value, let's just ask, it's the sample success count. So that is in the sample, what was the number of people who had your desired trait? That's what they're asking for there. So I look back at my sample. Hi, sweetie. Hi. Is Lucy down here? She's in her kennel. Okay, sorry. Then if I'm looking at my sample, what is the number of people who in my sample? Michelle, do you know what number we want to put in here?
Sorry, I was doing the test. What was your question?
Okay, so it asks us for an X value. It says the number of successes in the sample. And we're reading here, based on that 500, based on a sample of 500, 49 people own cats. So what is, I'm sorry?
So you are putting it into the calculator, or?
Yes, I'm trying to put all the information in the calculator. And it said, put the value from the null hypothesis. So I did.
Got it, okay.
And then it said, put the X sample success count. So what do I put for that? And I can scroll up.
500.
Now 500, it says a sample of 500, right? Is that my X value? And watch, the next thing they're going to ask me for is the N.
Yeah, so the N is the sample size. So N is 500, and the whatever the 49% of the 500 would be.
I think you said it just correctly.
49% of 500.
Exactly. That's what our X is. It's the number actual, because they give us the proportion of people in the sample who have cats, but they don't give us the literal number of people who have cats. And to find that out, we have to find out what is 49% of 500, sorry. So we do 0.49. Good, Michelle, times 500. It's 247 or 245. So now I put in 245. Now here is my information here. So this is kind of, with the TI-84 calculator, it'll make you choose, do you want this one, or this one? But with this test, it just does all three for you, and just is like, well, whatever you want, you can look at and get. So we have to match this symbol with the symbol in the alternative hypothesis. So if you look back at the alternative hypothesis here, I have this symbol, and it is facing toward the alligator's mouth is facing toward the left. So I just have to go back over here and find out which alligator's mouth is facing to the left. It is this one. So this is my p-value that I want. And it's 0.00002. So this is extremely small, right? This is like no dimes, no pennies, no tenths of a penny, no hundreds of a penny, and just 2/1000ths of a penny. This is a very small number. So it asked me, and then it asked me this Z statistic. And like I said, that's just something that the calculator spits out. Look, there is my Z statistic. And it says, does the same thing on the TI-84 calculator. It just gives you that answer. So it's just, you just get those points along with the p-value. So 4.1079. That's what we want there. And it says round to decimal point 4.1079, so it'd be 4.12, I believe. And then to calculate the pattern, and then say round this to 4 decimal places. And I think 1, 2, 3, 4, it's gonna be 0. Let's double check these answers. Yep, right on. Okay, so Michelle, now that we see our p-value and we actually know that the alpha is 0.025. So let me write the actual p-value and let's compare it to the real alpha. So it's the actual p-value is this value, and then this is the alpha, this is the p-value. So what conclusion are we going to make? We have to make a decision. Are we going to reject the null hypothesis?
Yes.
Yes, exactly. We're going to reject the null hypothesis because if the p-value is low, then the null hypothesis must go. And in this case, the p-value, and you might ask, well, what is low to you, right? Well, low is lower than alpha. So is it lower than alpha? Yes, it is. And one way that we can compare them, if you really are just not liking decimals, you can compare them by just you can add extra zeros after the decimal place until they both have the same number of decimal places. So that's 1, 2, 3, 4, 5 numbers after to the right of the decimal. So I have to add 1, 2, 3, 4, 5. And now we can just completely ignore any preceding zeros and any decimals. You just ignore it and you now compare these two numbers. This is like comparing 2 to 2,500. So which one is bigger, 2 or 2,500? 2,500 is certainly bigger, and that's the same for the same reason why 0.025 is much bigger than 0.00002. So yes, we say the p-value is less than alpha. If the p-value is low, the null hypothesis must go. So we reject the null hypothesis. And what they're telling us is they're saying, I mean, I missed the picture. The picture was, I erased the picture, but they're saying that in this distribution, in a population that has 40% of people that have cats, it's so extremely unlikely to get a sample of that large. That's a large sample, 400, 500 people. That a sample that large is probably going to be extremely close to the actual population proportion, 40%. And getting that large of a sample, like 49%, that probability of getting a sample like that is so extremely small. If we write this as a fraction, I mean, it's 2 in, I think 2 in 10,000. There's a chance every 2 times in 10,000 times you'd expect a result like that. So it doesn't happen very often. It is a very, very, very unusual event to happen. if the true population proportion is 40%. So it's evidence against the null hypothesis, and we're definitely rejecting the null hypothesis. And then what will be our final conclusion here?
I have supposed to wear glasses.
Okay. Make it bigger. If I can.
Let's see here. So
That didn't really help, I don't think.
it's okay. So the p-value is smaller than the alpha. So
We reject
would-
the null hypothesis.
yeah. So I would say there's not sufficient evidence.
Now, careful here. Now, here's the rule. If you say we do not reject the null hypothesis, then you're going to also say there is not sufficient evidence.
Okay. So then, okay, so because you're rejecting, so what was the original
Null,
hypothesis? What was the original hypothesis?
the original null hypothesis, that's why it's important we can't write it. We write it all down when we're doing these problems. That the proportion, and really we can think in our minds, and I was taught it's always equals. It's just we don't have to really worry about equals to or greater than, and that, in my opinion, I don't think we have to. So the null hypothesis is the proportion is equal technically or greater than 0.4, but we could just, it's easier for us to simplify in our minds, just p equal 0.4.
Yeah. Okay.
Hypothesis. So we don't think it's equal to 0.4.
Right.
I
So
mean,
the alternative one says that the proportion, is that a population or proportion?
this p,
Yeah.
now in the null alternative hypothesis, it's a good question. The p always stands for proportion.
Okay. That's what I
So
thought.
we're only going to deal with mean. So the mu,
Proportion. Okay.
and when they have that mu, they're always talking about mean.
Yeah.
And
Okay.
when they have a p, they're always talking about here proportion.
Okay.
And that's why we can actually, when you go up to the real problem up here, it says you can actually just like translate the null hypothesis literally straight from this, from the writing here. Proportion, right, your p.
Okay, so the
Larger than, you face the alligator's mouth toward the p. And then 40%, right, you're 0.40. And there's your alternative hypothesis. Like it's just shorthand, you know, of
right.
exactly written there. Right.
Okay. So yeah, so the p was less than the alpha, right? Is that what we decided?
Okay, I see what you're saying. There's two p's in the problem, right?
The p-value and that p.
I'm sorry?
So there's the p-value and then there's the proportion p.
Yes, exactly. And they're totally two completely different ideas. The p here stands for population proportion that we're interested in, you know, and that's that we're really interested in how many people like own cats. That's the focus of that p, right?
Yeah.
And then the p-value we talk about later, that p here stands for probability.
Okay.
This one is all the area under the curve, and that's what we've been focusing on. We were in all of chapter 7, we were finding the area under the curve and using that normal function and finding the probability of getting a sample back like this, finding the probability of getting one single person who weighed more than something or whatever. Like those were all p-values. Well, every time we found when we found the likelihood of getting a sample, you know, that was greater than 49 or something like that, those were all p-values we were calculating in, I guess, chapters 8, I think. that the p-value is the area under the curve, the probability of me getting a sample like that.
Okay.
If this null hypothesis is in fact true. And if this null hypothesis is true, then most of the sample proportions are going to be equal to 0.4.
Mhm.
If truly, if you think about something that you're maybe passionate about, maybe it might help a little bit, but like, if there's truly, I'm not sure what a hot topic is, I feel like, but like if there's truly 60% of people that don't want to be vaccinated or whatever, and if I take a sample of 500 people and I find out there's only 30% of the people that don't want to be vaccinated, I would question my belief that truly 60% of Americans wanted to be, don't agree with vaccinations. Why didn't my sample, why isn't it closer to the truth of how people are feeling about vaccinations? It makes you question. And you're like, well, maybe I got it wrong. Maybe there's actually a lot less people that are opposed to getting the vaccination or whatever. I'm sorry, I may have mixed it up. I kept going opposed to vaccinations and not opposed or whatever. But hopefully did that make sense to you?
To distinguish the P's, yeah, I think I'm on board with it.
So here in the null hypothesis, and really in this whole problem, we're really focused on what is the population proportion, and is it different than 40%? And the way we're going to prove that is by using something called a p-value, and the p-value is the probability of getting a sample back like that if the null hypothesis is true.
Okay.
Mm-hmm.
So then can you scroll down a little bit then to see the
okay, so we say we reject the null hypothesis. Now we reject the null hypothesis.
Yeah.
And then now what we always say in this final statement is, if we reject the null hypothesis, we say there is sufficient evidence. We always say that, and then we just state whatever the alternative hypothesis is. So proportion who own cats is larger than is larger.
Right.
Right, because it's exactly because this is our ulterior hypothesis.
Yeah.
Proportion larger is larger. And so all they did was just, write that alternative hypothesis in, they turned the P back into the word proportion, and then turned that inequality symbol back into a word.
Yeah.
Larger, right? But they should have said larger than 40%.
Right.
But that's okay. They said is larger. That's fine. So the reject null hypothesis always goes with there is sufficient evidence.
Okay.
The alternative hypothesis is true.
Okay.
Mm-hmm. And it kind of will help you too if you don't write fail. If you say we. Another way to say fail is just to say we do not reject the null hypothesis. The H sub O, the old null hypothesis, we do not reject the null hypothesis. Then if you rewrite fail as we do not reject the null hypothesis, then you can think about the not here matches with the not sufficient evidence there. Those two will always go together.
Mm-hmm.
If we do not reject the null hypothesis, there is not sufficient evidence. Because that's our big kicker. We really are hoping to reject the null hypothesis. And this is very similar to like the court of law. And I was talking to another student that like in the court of law, the null hypothesis, do you know, if you're like just in a courtroom, what is the null hypothesis? What are they assuming to be true until otherwise proven?
Guilty.
I'm sorry?
Or is it innocent?
Innocent.
Innocent.
Exactly.
Oh,
It's innocent, right? This is, we're gonna assume the person is innocent. That's the null hypothesis. They're innocent.
mhm,
And then what's the alternative hypothesis?
that they're guilty.
They're guilty. And so notice how in the final statements, when what they do is they always say, they'll say there is sufficient, they don't really use sufficient evidence, but I'm gonna add that in. If there is sufficient evidence that, and they always say either not, they're gonna say there is sufficient evidence that the person is guilty, right? Or they say, they don't say it exactly like that, but they always just say, what I mean there is they always just say either guilty or not guilty. They always have it when they state their final arguments, they always are like, there either is sufficient evidence to say the person is guilty, or there's insufficient evidence. There is not sufficient evidence to say the person is guilty. So it's either, not guilty or guilty, but they never say, hey, they're innocent. So in a very similar way, this is the ulterior hypothesis. So they always write that ulterior hypothesis in the final sentence. And so it's always like, hey, we have sufficient evidence for the ulterior hypothesis, or we do not have sufficient evidence for the alternative hypothesis. But they never say anything about the null hypothesis in that final statement. Are you okay with that?
Yeah.
And it's because we were assuming the null hypothesis was true. So for us to say like, oh yeah, the null hypothesis is true, you're like, yeah, but you did all your you did all your data like assuming that was true. So I don't know. Yeah, it's not it's not, they just don't want to write it like that. But does it make sense?
Yeah, no, that definitely makes sense.
Awesome. Okay, I think I'm gonna stop this recording. This will be the longest recording. They're like,